Okay, guys, this is a continuing wonderful sequence of online lectures that I'm putting together. You're probably amazed at the amazing high production values associated with these lectures, and well, you should be, because this is pretty impressive. I'm impressed. What we're going to do today, enough of nonsense. What we're going to do today is probably the most important part of matrices, or our analysis of matrices. Or analysis of linear algebra. That's the coffee machine, not me. Okay, it's going to turn stuff off now. Yep, it waited until I sat down and then decided to do something. So this stuff is going to be very, very important, because all the amazing software that you're going to encounter as you go through engineering is based on the analysis of the different systems that you're going to be doing is based on this particular idea of inverses of matrices. And it's inverses of square matrices. If your matrix isn't a square, you don't have what's called an inverse. So the matrix has to be a square. So let's assume, let A be a square matrix. Now, hopefully I won't be an idiot and ask you to give you a matrix in the exam and ask you to get the inverse of it if it's not a square matrix. And, because that would be, hopefully it won't, sometimes I just lose touch with reality when I'm writing exams, and I might ask you something stupid, but hopefully I won't. But just be aware, I can be an idiot. So let's, before we begin, A has to be a square matrix before any of the stuff that we're going to do today works. It has to be square, okay? So let A be a square matrix. Now recall, you don't recall, but let's recall what the matrix I is. Remember the identity. I is either 1, 0, 0, 1 is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1 is equal to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, etc. So I is the identity. It was called the identity matrix. And what it is, what form it has depends on the context. So if you're dealing with 2 by 2 matrices, I is the first one. Is this one here? This is 2 by 2 matrices. If you're dealing with 3 by 3 matrices, then I means this one. 4 by 4 matrices, you're talking about this one, etc., etc. So if you've got a 10,000 by 10,000 square matrix, then I in that case means this matrix here with 10,000 rows, 10,000 columns, but with ones along the main diagonal and zeros everywhere else. So that's a very, very important idea. So and this takes a little bit of getting used to what I actually means. Like, it depends on the context. And that's kind of, this may be the first time you've seen this in mathematics, where the same notation refers to different things depending on the context in which you're in, okay? So let A be a square matrix, okay? Then the inverse of A and we denote that by A, matrix A, with A, capital A, with a bar under it, to the power of -1. Now, folks, this -1 is not -1. It's just stupid notation. So if you see an inverse and a power of -1, it just means the inverse of A. Then the inverse of A is the matrix, is the square matrix, such that A inverse is equal to A inverse A is equal to I. So if A is a 2 by 2 matrix, then you're going to get this one up here. If A is a 3 by 3 matrix, you're going to get this one here, etc., etc. Now, if you look at this idea here, I remember doing this linear algebra stuff when I first went to college a long time ago, and I just did not go for this at all. Okay, I just did not like this at all, but it's a really important idea. And the important idea is that this equation here is general. It's completely general. It doesn't matter what the dimension of A is. You always get this result. But the important thing to realize, folks, is that if you're dealing with 2 by 2 matrices, it's just you're dealing with I here. If you're dealing with 3 by 3 matrices, it's this, it's in this. So this equation here refers to all square matrices, but I depends on the context. If you're talking about 2 by 2, it's this, 3 by 3, it's this, etc. All right. So the question then arises, well, how do you get A inverse? Okay, so you've got a matrix A. Suppose we'll do an example in a second. You've got a matrix A, and okay, A inverse it has this property here, this really, really nice property. But how do you get A inverse? That is not easy. Okay, so let me just turn the page over here. And can I write in this? Is this too? Yes, no, it's probably not good. All right, let me just write here. So finding A inverse. And it's really hard, actually. Finding the inverse of a matrix is really, really difficult. In engineering mathematics today, folks, a lot of research has been going on for the last 50 years, and it's still ongoing, actually, as to how you get the inverse of a matrix, all right? Because it is difficult. Now, and the formula that you use or the recipe that you use depends on the size of the matrix. That's really important. The same formula doesn't work for every single matrix. Now, for 2 by 2 matrices, it's easy, as we'll see. Okay? For 3 by 3 matrices, it's difficult. 4 by 4 and bigger, it's impossible, really. It's very, very difficult. You know, life is too short to invert a 4 by 4 matrix. I've never seen anybody do it. You know, so it's really, really difficult. We're going to be doing 2 by 2 and 3 by 3. And again, 2 by 2 is easy, and you need to kind of get that into your brains. 3 by 3 it is difficult, as you'll see. The recipe there's a few steps involved in the recipe, and it's not easy. We're not going anywhere near 4 by 4 because it's just impossible. It takes too long. Life is too short, as we now know, actually, in recent days. Okay, so we're going to focus on 2 by 2 and 3 by 3, and even the 3 by 3 matrix, folks, to be perfectly honest, I'm going to give you the recipe for it. We're doing it because I did it in college, and every engineering student does it in college, and that's the reason. There really is very, very little justification for this because it is. But the recipe, I suppose, one of the reasons why you're doing it is because it's an algorithm or a recipe that's an interesting kind of idea. It's an interesting kind of rigmarole, interesting sequence of operations. That you might use in other contexts. But really, there's very little justification for it. Basically, the justification is, I did it, so you're doing it. That's the way it works. And it's like your parent, it's my house, my rules. Okay? So let's do an example. Now, as I say, 2 by 2 matrices is easy. Now, so let's go up here. If A is 1, 2, 0, 4, find A inverse. All right. So guys, here we go. So you've got a 2 by 2 matrix A, and you have to find the inverse of A. Now the inverse of A would always be of the same size as the matrix that you're starting with. Okay, it's very important. So if A is 1, 2, 0, 4, it's a 2 by 2 matrix. A inverse is going to be a 2 by 2 matrix. There's a two-step process here. The first thing you do is you get the determinant of A. You always must get the determinant of A when you're calculating the A inverse. And this is true for any size matrix. The very first thing you do is you must get its determinant. Now, in this case, the determinant of A is, remember this, 1, 2, 0, 4. This is the notation for the determinant. Remember what it is. It's 1 by 4 minus 2 by 0, which is 4. Now, the dog is barking now. That's the dog barking. And my children who are here at home, basically watching Netflix while looking at the internet on the iPad, couldn't be bothered to get up and look after the dog. This is my life. This is the way I'm going to kill them. All right. So the determinant of A in this case is 4. And that's good. Remember we talked about this last day. The most important number for the determinant is 0. And it's either the determinant is either 0 or not 0. In this case, 4 is not equal to 0, which is great news for calculating the inverse. If the determinant of A is equal to 0, there is no inverse. You cannot find its inverse. Okay, so you just walk away. That is an extremely important idea. So if determinant of A is equal to 0, for any size of square matrix, there is no inverse. You cannot solve that problem, you walk away. Now in this case, because the determinant of the matrix is 4, it's not 0, you can find the inverse. So here's how you get the inverse. Now watch this, babies, because this is not obvious. It's 1 over the determinant, and the determinant in this case is 4. So it's always 1 over the determinant. You get a 2 by 2 matrix here, and here's what you do. Look up here now, you beautiful things. The main diagonal elements for A, you interchange. So this is 1 and this is 4. So the 4 comes up here and the 1 goes down here, because this is what you do. And you change the sign of the non-diagonal elements. So the 2 becomes -2 and -0 is 0, and this is what you get. Now you can leave it like that, and that's fine. If you want to multiply in by each of these elements here by 1/4, you can do that as well. It doesn't matter. In this case, what you get is 1 minus 1/2, 0 and 1/4. So this is fine, and this is fine. Whichever turns you on, whichever way you feel is happier with, go with that. Okay? But usually people just leave it like this, and that's fine. Now, in the exam, if I ask you this in the exam and there's a kind of a multiple choice element, sometimes I'll multiply in, sometimes I won't. So be prepared to multiply in by the number here. And remember what scalar multiplication is for a matrix. You multiply each element by the number, or in this case, you divide each element by the number 4. Okay? Now, what's very, very important, guys, is that you check your answer. Always check your answer when you're calculating inverses. So the way you check your answer is you multiply A by A inverse. So here's your check. A by A inverse. Excuse me. Hopefully that's not what we all hope it isn't. That's 1, 2, 0, 4. That's A. A inverse is 1 minus 1/2, 0 and 1/4. And we're going to get a 2 by 2 matrix here again, because this is 2 by 2 and 2 by 2. You always get 2 by 2 matrix. And then what you do is you do the ordinary matrix multiplication. So remember now, to get the first column of the product matrix, you're focusing on the first column of the second matrix. And you're going to multiply each row by the first column. So you're going to get 1 by 1 plus, that's 1 by 1 plus 2 by 0. And then you're going to get 0 by 1 plus 4 by 0. Okay, so to get the first column of the product matrix, you just multiply 1 by 1 plus 2 by 0 to get this element here. And then you multiply this row by this column, and you get 0 by 1 plus 4 by 0. Then to get the second column, you look at the second column of the second matrix, and it's 1 by minus 1/2 plus 2 by 1/4, which is 1/2. And then 0 by minus 1/2 plus 4 by 1 over 4. And when you do that, then you get 1, 0, 0, 1. Happy days. That's what you should be getting. You must get the identity matrix when you do that. So you can either do A inverse or A inverse A. Doesn't matter which you do. You're going to get the identity matrix. Okay. Now, boys and girls, that's a very important little recipe in mathematics. It really is. That's a very important little idea. It's an interesting programming problem. Those programming nerds amongst you, hopefully there are some. It's an interesting little idea. You know, how would you set that up in a little C program or a C function to do that? Okay, it's relatively straightforward, but you have to remember it. So none of this stuff is difficult, as we talked about our very first briefing together, moments together before we went virtual. None of this is difficult, But the problem is that there is a lot of it. Okay, so every single lecture we do, there's a new thing. You need to keep on top of this. You need to do the exercises on loop. Now, with regard to the exercises on loop, you may have noticed that I put up a solution to one of the problems, because some of you emailed me and said, well, what's the solution to this problem? And I did it because I'm very obedient. If you're having problems with any of the exercises, you can email me. Now, I obviously can't answer all 170 of you if you decide to email me. But what I'll do is, if there's a couple of emails or 3 or 4 emails asking the same question, then I'll do that and put it up on loop. Okay, that's the best I think we can do. All right, so that's the A inverse for a 2x2 matrix. Now, we did it in terms of numbers. Now, don't be afraid if I ask you something like this. Okay, so some people might shy away from this because it's not numbers. It's like cosines and sines, but it doesn't matter a damn what it is. Like this could be, sheep and cattle. It doesn't matter what the entries are. The recipe is always the same. So do not be fazed by this. Again, when I was your age, I was, and I have to admit this, again, I said to you before, I didn't have any friends, and I was very intimidated by this. Most of you don't have friends, but let's hope that you won't be intimidated by this now. Don't be intimidated by this, because this is very straightforward, really. It's exactly the same recipe. So the first thing you do, guys, remember, is you get the determinative A. So the determinative A here is, can I write C for cos theta, S, and minus S and C? Okay, so C stands for cos theta, and S stands for sine theta. So I want to get the determinative of that, folks. So what the way I do this, C by C, so I'm going to get cos squared minus, and this by this is minus sine squared. So you get cos squared plus sine squared, and that's equal to 1. Always. The most important identity in trigonometry. Cos squared plus sine squared is equal to 1. If nothing else from this year, guys, okay, you've learned the terrible effects of isolation and living with your families, perhaps when you thought you had escaped, but now you're back and you have to suck it up. But that you've learned that it's, but this is the most important thing. It's a really important little idea. It happens. It's amazing how often this happens in engineering analysis. Cos squared plus sine squared is equal to 1. Do not forget that. It simplifies things dramatically in many cases. The next thing you do then, folks, is you get A inverse. Remember what we said? It's 1 over the determinant. The determinant in this case is 1, so it's 1 over 1, and 1 over 1 is 1. Now, remember what we do. We interchange the two elements here. Now, so you put this cos theta goes there, and this cos theta goes there. So essentially, we have cos theta and cos theta again, because they're the same. So when we interchange them, they're the same. But we must change the sign of the off diagonal element. So this becomes minus sine theta, and this becomes plus sine theta. Okay? And then remember what you have to do always, do not forget to do this, is you must check. So A inverse A is, let me write C minus S, SC. And then remember what A was. A was CS minus SC, where C stands for cos theta and S stands for sine theta. And so when you and remember now we for A inverse here, 1 over 1 is just 1, so we can ignore that. So this is what you get for A inverse. So when you multiply that out, guys, let me do it here. You're going to get cos squared, and minus sine by minus sine is plus sine, so you're going to get cos squared plus sine squared. Here you're going to get cos SC minus SC. Up here you're going to get SC minus SC, and down here you're going to get cos squared plus sine squared. And you get cancellation here, and so you get 1, 0, 0, 1, as you should. So this kind of idea, guys, if I give you a matrix with non-numbers in it, with symbols in it, the recipe is exactly the same. Do not be fazed by it, okay? Because it's a very important little recipe to get into your brains. Some of you might have done this before in secondary school, and you're seeing this for the second time, but it is a very important little idea. I use this, again, in my stupid corner research world. It's amazing how often that you have to do this kind of inversion, and even with the 2x2 matrices, how often you have to invert 2x2 matrices. It's amazing. All right. Now, boys and girls, where it gets tricky, and it does get tricky, is if you have a 3x3 matrix. And I'm going to do the example in the book, although I don't know why, but I'm going to do it anyway. So the book says find the inverse of a 1 minus 2, 0, 3, 1, 5, and minus 1, 2, 3. Now, so let me just remark here. So this is a 3x3 matrix, and inverting a 3x3 matrix is it's difficult. It's just long-winded, and it's, there's a few things you have to do, and it's just not great. Okay, but I'm going to say I'm going to do it and show you how to do it, and then if you want to do a 4x4 matrix, it's a generalization of what we're doing here for 3x3, but we're not going to look at that. So again, now guys, when I came across this the first time, I did not like it, but you just have to just do it. It's just a rite of passage, basically. It's like engineering parties. You have to go and suffer them because that's what you do. All right, this is exactly the same. All right, the first thing you do, guys, as always, when you find the inverse of a matrix, is you get the determinant. Always the first step. If the determinant is 0, you walk away. You cannot find the inverse of the matrix if it's determined to 0. And remember, we talked about this before. Another way of saying the determinant of the matrix is 0 is that the matrix is said to be singular. Again, a stupid terminology that you have to put into your brains, but you will see this actually. Matrices being singular, you will hear people saying this as you're going through your engineering education, and you may wonder what it is. Don't wonder. The matrix being singular means its determinant is 0, and following on from that, it means that you have no inverse for it, and that has implications for engineering analysis. But we don't care about that at the moment. What we care about now first is getting the inverse of a 3x3 matrix, and the first thing you do is you get the determinant of A. So in this case, look, let me do the determinant of A here. So it's 1 minus 2, 0. It's 3. That's a 3. 1, 5. And that's minus 1, 2, 3. So remember what we did this the other day, guys. It's the stupid things that you have to cover up and whatnot. So you write down the first element of the first row, which is 1, and you must multiply it by the determinant of a 2x2 matrix. And here it is. You cover up the first row, and you cover up the first column. Ooh, look at this, look at that. It's just amazing teaching technique here. I used pencils. This came to me there. So what you do there, folks, is you get the determinant of that. So it's of that 2x2 matrix, it's 1 by 3, which is 3, minus 2 by 5, which is 10. Okay? That's the first thing you do. And then what you do is you change the sign of the second one, so it's plus 2. And I cover up the first row again, and the second column in this case. And when I do that, I get 3 by 3, which is 9. And then minus 5 by minus 1, which is minus 5. Be careful with the minus signs. And the last one then, I have 0. I don't care what I multiply by 0 by here, because if you multiply by 0, you get 0. So when you multiply that out here, folks, you get minus 7, I think, is that right? Minus 7, yeah. Plus, that's 14 by 2, which is 28. And I'm getting 21, which is not equal to 0. So we are happy. Okay, so we can find the inverse of this matrix. Okay, so that's the first thing you do. Now, before we go on then, we have the second step. We have to get the transpose of this matrix, bizarrely enough. So the next thing then, to calculate the inverse of a 3x3 matrix, after getting the determinant, we then get the transpose. So this is step 2. So A transpose then is, remember what happens? The rows become columns. So the first row, which is 1 minus 2, 0, becomes 1 minus 2, 0. The second row becomes the second column, 3, 1, 5, and you get minus 1, 2, and 3 here. Okay, so this was A, and this is A transpose. Okay, so the first row becomes the first column, the second row becomes the second column, and the third row becomes the third column. Then what you have to do, folks, is you have to to get what's called the adjoint matrix. What you have to do then is you have to imagine, or not even imagine, you have to use what are called the place signs of a 3 by 3 matrix. So this is step 3. So the place signs, we've seen this already when we're looking at the determinant of a 3 by 3 matrix. But each element in a 3 by 3 matrix has a plus sign or a minus sign associated with it. This is the way God made this. I don't know. I'm just a messenger. All right. But the place signs of a 3 matrix are like this. So the first element in a matrix is associated with plus. The second element is minus, and the third element here is plus. So we've seen this before. We've seen this when we were looking at the determinant. Remember? Yeah. So the first we wrote down the first element here. We changed the sign, so we got minus 2 to get plus 2 here, and the third element was 0, so we didn't do anything to that because it was 0. But that's essentially what happens. And then, guys, it alternates. So plus, minus, minus, plus, minus, and then plus, minus, plus. I know, I didn't make this up. I'm just telling you what the news is. Okay? So we're going to be using the place signs here. Okay? And then what you do then is you calculate what's called the adjoint matrix. I know. So the word adjoint is abbreviated in mathematics as ADJ. So the adjoint matrix of A is the following. Now wait for this, folks, because this is not obvious, all right? This is not obvious at all, but let me show you what to do. What you do is you go to the transpose matrix. Now this is very important. You don't go to the original matrix A, which is here. You go to its transpose. And to get the first element of the adjoint matrix, here's what you do. You cover up the first row. Let me use the pencils because they're fabulous teaching aid. And the first column of the transpose of the matrix, and you get the determinant of the resulting 2 by 2 matrix. All right? So in this case, you get 1 by 3 minus 2 by 5. Now, the adjoint matrix is also a 3 by 3 matrix. Okay, so that's what you do there, folks. So you get 1 by 3 minus 2 by 5. You get the determinant of the resulting 2 by 2 matrix when you cover up the first row and the first column, because I want the entry here. For the second entry here and the second entry in the second row, what you do is you cover up. You leave the first row covered up, but you cover up the second column here. So you get minus 2 by 3 minus 2 by 0. Now, you have to be careful here. Can I come up here? Because I don't have enough room. Sorry. So you get minus 2 by 3 minus 2 by 0. Right? So it's this by this minus this by this. And so what you end up here is you get minus 6. But because the place sign associated with this entry here is minus, you must change the sign of this. So this becomes plus 6. Okay, and you think, oh, what? This can't be right. It is right. This is what you do, folks. Now, if you look at the next entry here, you see the sign here, the place sign associated with this element here is plus. So we don't have to do anything messing around with the minus. So all we need to do is get the determinant of this. So it's minus 2 by 5 plus or minus, sorry guys, it's minus 2 by 5 minus 1 by 0. Okay, now let's get this element here. So it's the second row and the first column. So what you do is you cover up this and this up here. Hopefully you can see that. You cover up the second row and the first column, because that's the element we're talking about. Sorry, if I can balance my pencils. God love me. And so what you're going to get here then is you're going to get the determinant of this matrix, of the 2 by 2 matrix here first, but you must change the sign, okay? Sorry. So what you do here is you 3 by 3, can I just come over here? So you get 3 by 3 minus 1 by 5, which is minus 5. So that's 9 plus 5, which is 14. But because the minus, the place sign associated with this element here is minus, you must change the sign here, and this becomes minus 14. Okay? That's the way it works. Okay? The next element here, the place sign is plus, so you just get the determinant. So it's 1 by 3. So if you can see up here, guys, it's 1 by 3 minus 1 by 0. Minus 1 by 0 is 0, so you just get 3 here. And then the last one then is this matrix here. It's 1 by 5, which is 5, minus 3 by 0, which is 0. So you get 5 minus 0, which is 5, but you must change the sign because it's minus place sign. So you get minus 5. All right. And the last one then, we're all running out of the will to live here. All right. So this is the last entry here in your adjoint matrix is this. Is you get a 3 by 3. So you want this entry here. So if you cover up in your transpose matrix, you must cover up the first column and the last row. You're left with this matrix here. It's 3 by 2 minus 1 by minus 1, which is minus 1. And because the place sign is plus, you just leave it as it is. The next entry then here, guys, is, can I come up here and do it up here? So it's 1 by 2 So 1 by 2 minus 2 is 0. And because this is a minus sign, you must put a minus sign in front of this. But minus of 0 is 0, so you just get 0 here. And the last one then, guys, is this, because the plus sign is plus, so it's 1 by 1, which is 1, minus 6. So when you do all this calculation here, for guys, you'll see that the adjoint matrix then is, okay, sorry, the adjoint matrix then is, if you look at here, the first entry is 3 minus 10, which is minus 7. So this is minus 7. It's 6 for the second entry here. This entry here, we said was minus 10 because the place sign is plus, so it's minus 2 by 5, which is minus 10. We said this entry here is minus 14. This entry here is 3. This is minus 5. And the last one then is 6, 0, and the last one entry there is 7. Actually, folks, I don't think that's right. This entry here, look, it's 3 by 2, which is 6, and 6 plus 1, is 7. So that's 7. So that's the adjoint matrix. We've calculated the adjoint matrix. And then finally, folks, here's step 4 in the never-ending calculation. A inverse then is 1 over the determinant. And remember what the determinant of A was. It's 21 times the adjoint matrix, which in this case is minus 7, 6, and minus 10, minus 14, 3, and minus 5, and 7, 0, 7. And step 5, which I'm not going to do because I basically, it's just too much trouble. But you must do this. If I ask you to do this in the exam, definitely do this. Check your answer. So make sure that when you multiply A by A inverse, you get I, which in this case, because we're talking about 3 by 3 matrices, will be this. Make sure you do this. Now, because I am old and cranky, I don't have to do it, apparently. I can get away with it. But because you're young and beautiful and not cranky and you're full of hope, you have to do it. That's the way it is, okay? So you must do this step. You must check that your answer gives you the identity matrix when you multiply with the original matrix here, A. All right? Now, let's recap. 2x2 matrices are easy to invert, and it's very, very important that you do that. 3x3 matrices are very difficult to invert. It is examinable, but it's not crucial to your engineering education. Do it. Be able to do it. There will be marks for it in the exam. But in terms of understanding and getting recipes into your mind, the 2x2 inverse is the one that you should be focusing on. That's the one for sure you need to know, because you will see this over and over again when you're doing engineering analysis. So why not just get jiggy with it now? Yeah? Why save yourself some disappointment in the future and bitterness, and just do this? Okay? So now, guys, that's basically it. Next week, we're going to start actually applying matrices to solving equations, which is really important because that's the whole point of doing this. What we've done so far is just arsing around with matrices, but I want to show you the use of matrices in solving equations. Now, you may think that solving equations is no big deal. It is a big deal in engineering. It is what engineering is about, after all. So, yeah, come back next week. Study hard. Have a good weekend. Stay safe. No touching. We've talked about this already. And yeah, keep your distance. All right. And I'll talk to you next week. Goodbye, guys.